So, welcome everyone. Thank you for getting up early after this party and to attend my talk. I really appreciate it. My name is Reginato. I work at Tetran, and today I will present you an updated analysis of PatchGuard on Windows 10 Redstone 4. So, here is a summary. First, there will be an introduction where I will present you what this talk is about, a quick overview of what PatchGuard is, and our approach to analyze it. Then I will talk about PatchGuard initialization, how it triggers a check, how verification routines works, and I will discuss a proof of concept that I implemented to disable it, and finally I will conclude. So first, the introduction. What this talk is about. My objective here is to cover main mechanisms of PatchGuard, so you can get a global understanding of how everything works, so you can go and disassemble it and watch what I found. There will be an incoming white paper, and I hope some code, if I'm allowed to. There will be much more details in it. Here I only have like 45 to 1 hour, so it's difficult to explain all of it. There will be some known stuff, since PatchGuard is basically use an incremented way of developing. So basically, most of it are from Windows 8.1, but there is some new stuff from Windows 10 and, of course, some results. So what's PatchGuard? Originally, it's called kernel patch protection, but nobody calls it that way. I don't know why. It first appeared on Windows XP x64, and the idea is that it will scan kernel for patches and trigger a blue screen of death if it detects a modification. For example, there are some structures such as the IDT, the GDT, some debug routines, the list of loaded module, and PatchGuard itself that are protected. There is a non-exhaustive list available on the MSDN if you look at the bug check 109. So, what's the objective of PatchGuard? PatchGuard will prevent malware on our commercial products from tampering with the kernel. The idea is that Microsoft realized at some point that most of the report crashes that they got were from malware on our third-party drivers. So they decided to prevent this from happening. In case of malware, for example, malware would like to maybe hook some functions to enumerate process so that it will hide itself. And for commercial products, you can get some, for example, hook on create process so that the antivirus, for example, can analyze something before the process is launched. And in this way, it might occur that these patches are quite ugly. So Microsoft decided to prevent that. PatchGuard runs at the same level as any driver, which means that theoretically, any driver can disable it. Which seems true theoretically, but the thing is, it's quite difficult now since PatchGuard use a lot of techniques to hide itself so that you can just find it and disable it. So right now it's quite difficult, but in this presentation I will show how PatchGuard initializes itself in many ways and how to disable each ways. So here is a main mechanism overview. It's a very overly simplified diagram, very overly simplified. I mean, it's just for explanation. First, there is the initialization, which occurs at the beginning of the boot, before any user driver, so that, of course, there is no possibility to hook stuff at this moment. The idea is that it will harvest necessary data and store it for later use, and then it will hide itself. Basically, it's a slip, but it will do it in a hidden way so that an attacker cannot just find it and disable it at this moment. Well, actually, if you reverse it, you can find where it's sleeping. Then, regarding an event, a check will be triggered. For example, an event may be a timeout that comes to expiration or some other stuff, but it's just an event. And regarding the result of the check, there will be two possible outcomes. The first one is the modification is detected, and the second one is integrity check failed, and it will trigger a blue screen of death with bug check 109. So what's our approach for this? We used timeless analysis. So basically, we developed a driver to patch the IDT and record the initialization with on the blue screen of death with Raven, which is a timeless analysis tool that our company developed. And then we analyzed the detection algorithm. By going back in time, we could easily find interesting data, such as encryption key and other stuff like that. And basically, we got a good overview of the whole PatchGuard structure, which is used all along by PatchGuard. And this good overview allowed us to use static analysis and combine with timeless analysis later to point out a specific mechanism. So here's the introduction. Now, what about the initialization? The initialization is performed by mostly by KI filter fiber context, which is a node function. This name is originally here to prevent a reverser to know what it's doing. So it's trying to maybe hide itself with an unrelated name. And this function is called in two manners. The first manner is by KI init AMD64 specific state, and it will use some tricks to call KI filter fiber context. It won't just call it directly. It will trigger an exception handler with a divide error. But this divide error is built in a specific manner, such as it will use two global variables, which are KD debugger not present and KD pitch debugger. And you may guess that basically, if PatchGuard detects a debugger, then it will not be launched. So this is a nice divide error. So once this happens, the exception handler is triggered, and in the exception handler, there is a call to KI filter fiber context. And this call is particular since it has a 0 parameter, which gives a good hint about the fact that it's called elsewhere. And the fact is, it is. It is by X license watch init worker, which is called at the very beginning of the boot in phase 1 initialization. But once again, there is some tricks to hide itself. X license watch init worker we call KI filter fiber context with only a 4% chance. This is interesting because it also means that if you think that you disable PatchGuard because you disable some method, maybe you didn't disable this one, so maybe your computer will crash 1 out of 100 times. So yeah. In this case, a structure is passed as a parameter, which will allow new methods of initialization. So let's talk about KI filter fiber context itself. It's a small function. It has trivial checks of debug, and it will call KI init PatchGuard context, which is actually an unnamed function, but in literacy it's called this way by previous researcher. So I keep this name since it's pretty relevant. The thing is, this function will initialize a PatchGuard context and is actually called several times. So this means that at any moment in the system, there will be multiple PatchGuard contexts running. So if you disable one, there is probably another one running. The first call to this function will occur no matter what. The second call will only have 50% chances of occurring. And the third call is quite special. We will discuss it. There is also a notification of a callback, which is interesting. We'll see why. And there are two other methods that are not directly linked to KI filter fiber context, but I put it here because it's related to methods. So compared to Windows 8.1, these three methods are new. We'll discuss it. But I explained, I talked about PatchGuard context, but now I will try to describe what it is. In literacy, PatchGuard context used to describe a full structure that is used by PatchGuard to perform checks, random checks, and not random, to perform checks. And actually, most of the people tend to modify this name by also including the method that is used, because when someone say I found a PatchGuard context, they don't say I found the PatchGuard context structure, they say I found a whole process of PatchGuard. So I like to consider that the PatchGuard context is actually a combination of a method and a structure. So basically the method is all checked or initialized and triggered, and the structure holds every information that is necessary for PatchGuard to proceed with checks. So what about the structure? The structure is organized in 3 parts. There will be the first part, which basically hold decryption routine, which will be executed from this PatchGuard context structure, and some NTA API function pointer, which are necessary since the structure and the PatchGuard context will be allocated at random area. So to resolve function pointer, it will be maybe complicated. So basically, it's holding its own function table. There are some flags that are used all along and some runtime variables, such as, for example, the total amount of data that has been already checked on many other variables. The second part will hold some PTE, page table entries. Basically, PatchGuard will save them for later use, and we'll see how it is quite important. It will also save the full code of some anti-routines, such as KE bug check or KE bug check eggs. You may guess that also it's very important for later use. And there is also the full check of the check routines on some steps which are used by the check routines, which likely, like the user, is very important, so that an attacker cannot just hook the check routines because, for obvious reason, if you hook the check routines, then it's over. And the third part is very interesting because it will contain an array of critical structure data, which will contain actually all that is necessary for PatchGuard to analyze each structure. For example, it may look like this, like this structure. For example, there is the type of the structure, which is also the argument given to KE bug check. And for example, it's 2 if the IDT is modified, 3 if the GDT is modified. And there is also a pointer to the data, the size of the data, which are necessary to perform the checksum, of course. And there is the original hash that has been computed at the initialization time and will be compared after. And there are some specific values which are used depending on each structure that is checked. For example, for the IDT, these specific values contain the process number, so processor number, so that since the IDT is processor bound, this means that PatchGuard will need to execute on the same processor to get the same IDT. So basically, it may change regarding each structure. So regarding methods, it's how PatchGuard initializes and triggers a check. Most of them are initialized by KI init PatchGuard context, as I said before, but not all. For KI init PatchGuard context, what determines which method to use is actually the argument. And when I say many methods here, it means that given the argument, which could be one of these methods, which are 0, 1, 2, 3, 4, 5, 7, no 6. I don't know why there is no 6. I didn't know. And in this case, so the argument decides which method to use. So let's have a look to argument KI init PatchGuard context. For us, the two main arguments in this presentation, only because, of course, I describe them better in my white paper, but for this presentation, the two important arguments are the scheduling method, which basically is one of the 7 methods from before, and a pointer to the structure, which comes directly from the xFly.watch init worker, if you recall from here, basically, which only has a 4% chance of occurring. So let's have a look at each method. The first one use a timer with a DPC. So basically, PatchGuard will initialize a DPC, which is a deferred procedural call, on a context structure. And with KE set call escapable timer, it will set timer with it, which means that in system view, basically it will go in a kernel structure, which is a timer list entry, and it will add a timer to this list entry, which will be triggered regarding the due time. And basically, if you want to disable this method, you just have to go through this timer list entry and find the timer, the right timer, and set the due time to infinity so that PatchGuard won't trigger again. The next method are almost the same, method 1 and 2. Basically, it will use a DPC and hide it. So it will initialize the DPC and a context structure, but instead of queuing directly with the timer or else, it will hide a pointer to this DPC into structure in the kernel, which is a process register control block, which is usually used by the kernel to handle thread stuff on system stuff and scheduling stuff. And in this case, you can see that there are 2 entries, which are HL reserved and ACPI reserved. So now that, you know why there are some reserved parts in the Windows kernel. It's to hide PatchGuard. And in this case, the HL reserved or ACPI reserved will hold, may hold a pointer to a KDPC, which is a PatchGuard KDPC. What's interesting here is that the system, there is a system function, a legit one, which will actually queue this DPC at some point. For example, it may be regarding some transition to either state or other. And once it occurs, it will check if the HL reserve entry is zeroed or not. And if it's not, it will just queue the DPC. And it will just make a little check so that PatchGuard is not triggered too much. So it will only check that at least 2 minutes have elapsed since the last queue. Sorry. So method 3 is specific as it will use the structure, the 4% chance structure. So this method is pretty rare, but let's have a look at the structure that is passed to this method. Basically, this is a structure, and this method will only use 2 entries, which are a pointer to the PS create system thread function and a pointer to the stub to the check routine. So right now it's pretty simple. It will just create a new system thread with a stub to the check routine as a start address or the pointer to the context structure as a parameter. But there is an elegant obfuscation that is added that I wanted to point out. And what's interesting is that there were a null bypass that use to check the start address to identify a PatchGuard context. So a new version of PatchGuard modifies this PatchGuard context, modifies this PatchGuard entry in the start address entry, and puts a pointer to KE balance set manager or KE swap process or stack or export of thread on else, so that you can't identify a PatchGuard thread this way. So yeah, I found this obfuscation quite elegant. So method 4 will queue an APC, which is an asynchronous procedure call. It will simply initialize a context structure on an APC and insert it in an almost random system thread. Yeah, this one is simple. The 5th one is actually also quite elegant, in my opinion. It will use the specific structure, which has only a 4% chances of occurring. And this method will basically hook a regular DPC. So to do so, it will get a pointer to the global DPC, which is actually a legit DPC that is queued by the system every second or so. And it is queued by KE balance set manager. The idea is that PatchGuard will hook this legit DPC to queue its own sometimes. I said sometimes because basically there will be a counter that will be like 120 times around it. Usually it's 120 times and 130 times, so between this value. And when every 120 times, it will queue the PG DPC instead of the legit one. So it may be interesting also to look if you want maybe you yourself to hook this legit routine. So yeah. So the 7th one is one of the new one. This one is very interesting because at first sight it does nothing. Really, I looked at it and I followed it with timeless analysis step by step, and really it does nothing because it will initialize a DPC structure with a semi-random routine, and it will clear it right after. So for now, I have no explanation about this behavior in particular, but there is something quite interesting in the rest of it, in that it will initialize a global PatchGuard context structure. Basically, the structures that I talked about previously will be initialized in memory, and there will be a global pointer pointing to it. What's interesting is this global PatchGuard context structure is actually in clear text in memory. So if tomorrow you want to analyze PatchGuard and don't know where to start, basically I will tell you to start by watching to this PatchGuard context structure as it's in clear text in memory. So it's really a good way to start. So this PatchGuard context structure is actually used by the 2 new other methods. And this is where it may be interesting. The idea is that first the method callback. The method callback basically will set verification routine pointer into a global variable. And at this point, we may ask who created this callback in the first place. And with timeless debugging, we can apply to the object, and we go straight to MSSec FLT, which is related to Windows Defender Advanced Threat Protection. And this is actually the first time there when we can see a link between the MSSecFLT and PatchGuard. There is also the KISW interrupt dispatcher, which is almost new. It has been first seen by Artem Shishkin in a tweet. And it's called by KISW interrupt, and it's an IDT function, and it will use global PatchGuard context as well. The last method, well, not exactly last, but last method is CC initialize BCB profiler, and this one is quite special because it doesn't use PatchGuard context structure. It will only use a specific structure that it will ship itself and use itself. This one is quite small. It won't check the entire system. It will only check one specific routine from the NTOS kernel binary and check for its integrity. And this routine is actually a random one. One for each boot. So it's very, very rare, but it may occur, and it's not a problem. We disable it anyway. So now that we've seen the initialization, let's see how PatchGuard triggers the check. There are multiple ways of triggering a check. We've seen that there is the DPC, the system thread, the asynchronous procedural call, the KISW interrupt dispatcher, the global variable from MSSecFLT, and the CC initialize BCB profiler. So we'll go with the DPC, which is actually the historical one. Right now it's well documented, but I want to explain to you maybe in a comprehensive way. So here is what a DPC look like. It will first check whether or not the DPC is the pointer to the default context is no, sorry. It will first check if the DPC is a PatchGuard context one. And then it will trigger an exception handler, and then it will decrypt the structure, and finally it will pass control to the verification routine. So how it does this? The first thing it does to check whether or not the DPC is a PatchGuard context is to check whether or not the default context has a canonical pointer. So basically, if the pointer starts by FFFF, then it's canonical pointer, then it's not PatchGuard context. Otherwise, it is. In this case, if it is, then it will trigger an exception handler trick, which I like to call a Russian roulette trick. And here's why. Basically, there is a list of circular functions. Each function will call the next one on the list and decrement a pointer. And once this pointer is 0, then it will dereference an invalid pointer, which will trigger an exception handler. And in this exception handler, the context structure will be decrypted. And here, at this point, we want to know how it is decrypted. Well, at first, there were only one layer, but they realized that some attackers could retrieve it anyway by brute forcing and going through the whole memory. So they added some specification. So the first layer decrypts the entire context structure and let a header that is equal to CCCC. So basically, it's not very good. So it will rewrite the 4 first bytes. This is yeah, we will see about it. This is interesting because these 4 first bytes are actually self-modifying code. It will actually be executed right after. So basically, it will decrypt the rest of the structure, but will encrypt the 4 first byte with itself. And I want to just point out something about these 4 first bytes. As they are rewritten, they may be rewritten in different way. The first way is, for example, 1 by 1, and here you can see that yeah, the SOR instruction is written like this, but it also can use a SOR instruction, and also can use a rotation, so that you the origin of this obfuscation is probably because they don't want you to find magic value in the binary, so they hide the magic value, which is actually a 1-1 traband, etc. Yeah. So once this context structure is decrypted, basically it will pass control to the verification routine, but that's not as simple as it seems. First, it must perform some checks. Basically, it will check the PatchGuard integrity, PatchGuard context structure integrity, which is necessary to check whether or not an attacker has modified it during its sleep. And it will also check the integrity of 47 routines or part of routines, which, for example, are the epilogue of X worker thread or the exception handler of X worker thread, which are actually out points of that an attacker can hook and use to hook in one of the bypasses I know. With the attacker hooked this function to intercept PatchGuard before the check. So it will also initialize the work item, and then there will be 3 possible steps for the worker routine, which we'll call the verification routine eventually. So this was for the DPC. Now we will see the system thread method, and the first time the system thread method is called, basically the thread will wait on an event, and this event will be notified at the end of the initialization function. So basically, almost right after. Basically, the method, the rest of the method is the same as the DPC, but without the exception handler. So basically, now it looks like this. Yeah, next time will be timers as usual. Now that we see system thread, we can see the asynchronous procedure call. In this case, just like system thread, it's inserted as is, and it will execute directly the context structure decryption without any exception on their part and other stuff. So what about the KISW interrupt dispatcher? And for this case, it's very completely different, since there is no need to decrypt the context structure, since, as I said to you, this global PatchGuard context is actually in clear text in memory, so the call is quite direct, and passing control to the verification routine is possible. And finally, the CC initialize BCB profiler, finally, the global variable from MSSecFLT. This was interesting, is it's called only by sec-kernel integrity check, which is a function from MSSecFLT. And it's related to events triggered by the event tracing from Windows, ETW. And I can show you a call stack, which shows that it comes from some event. For example, this is one of the call stacks that may lead to the check routine, which is send file modify event. So yeah, basically, it's maybe triggered in different ways, and in this case, I only look at it statically, so there are a lot of possible call stack, and this is one of them. So, yeah. So one last method to describe is the CC initialize BCB profiler. In this case, there are 2 identical routines, almost identical routines, which will basically check, as I said, only one function per boot. So yeah, the check is done by itself, and then it will go to sleep by waiting on an object or delaying or a simple sleep. So now let's see how verification routines work. There are 3 verification routines mainly. The first one is the historical one. It's about 12 kilobytes. So it's pretty huge to rehearse, but you can have a look at it if you want. Basically, you just have to open NTOS kernel and disassemble it and look at the most huge function in the binary, and it will be probably this one or another one from PatchGuard. But basically, it's really, really huge. So it's quite complicated to analyze it. The second function is a check routine from the global variable, which is almost the same as the historical one, but there are no rearming part of PatchGuard. And the third one is a CCBCB profiler or non-name routine, which are identical, as I said, and it only check for a random routine, one per boot. So in our case, we will only see the FSRTL MD complete devx. And let's have a look at an overly simplified diagram of what it does. Yeah, so first there is a prologue. Prologue include this operation. Basically, there are some checksums, some re-encryption, some checksum again, await, some checksums, some recryption, and so on. And the idea is that all of these operations are done in one objective, which is protecting PatchGuard while it's waiting. And the thing is, PatchGuard will wait in the middle of the verification routine. So it will wait actually multiple times during while it's hiding and in the verification routine. So it can wait with 1 out of 3 functions. The first one is an unnamed function, is actually named self-encrypt, wait on decrypt in literacy. And there is a second one, which is KE wait for single object, and third one, KE delay execution thread. The choice of which method to use to sleep at this point is done from the initialization function. And each of these functions is called with the timeout or a due time between 2 minutes and 2 minutes and 10 seconds. And there is only one special case, which is when PatchGuard waits with KE wait for signal object. In the case where the object is actually already in a signal state. So in this case, it just won't wait and trigger the check immediately. So there is also something I want to point out, which is related to previous version. Previous version used to always execute itself on the last processor of, in this case, PatchGuard tries to randomize it a bit and will loop through all system on the thread, on the system, and pick a random thread and get a mask and pick a random, basically, not exactly, but basically pick a random CPU in this mask. So next, we'll see how checks works. As I said before, it will use data from the context structure. It will need the type of the structure to be checked, the pointer of the data, size of the data, the original checksum on some specific value. And there is also a size counter of all the data that has already been checked, and also the maximum amount of data to be checked, which is, at this point, you may have guessed the algorithm. So basically, here is how it works. There are several structures. For each structures, it will check whether or not it will need to perform some operations. And then it will compute the hash of the target with the size and pointer to the data. And it will compare it to the original hash that has been computed at boot time. And then if the total size of already checked data is less than the maximum size, it will just go with the next structure in its array. So let's have a concrete example. We followed the IDT case. And basically, as I said before, the target processor is stored in the data structure. So the first thing it does is basically to change its own affinity so that it gets the same affinity as the one that has been used at the initialization time. It will do so with case at system group affinity thread. Next, once it's got the right affinity, the check will be split in two parts. The first part is it will iterate through each KXNX15 interrupt, which is actually what I call the specific part. This is directly this specific of the IDT case. And then it will perform the checksum of the IDT, which is the more common way, since this checksum is the usual way. If when this check is performed, there will be two possible outcomes. The first one is rearming PatchGuard, and the second one is broad screen of death. So, when everything is fine, basically the rearming of PatchGuard will be almost maybe the same as the initialization part. So basically, it will, if you pick a timer for the method, basically it will reset a new timer with a random amount of time, and next check will occur 2 minutes later, basically. But if a modification is detected, then it will proceed to broad screen of death. And this is why we are gonna analyze, because most of some bypasses you used to hit at this point. So the first thing it does is a checksum of the context structure, but we analyzed this result, and we saw that actually it's never compared anyway. So I really have no idea why it's here. Maybe it's only so that Microsoft or any person will get it to maybe to check where in the crash dump, but this has no effect on the control flow. The second thing it does is re-encrypting the first part of the structure, but not the rest of it. So yeah, I'm not sure why it does this. Next, it will rewrite the page table entries with the saved values that if you recall, I explained at the beginning from the second part of the PatchGuard structure. Yeah, this is done because, of course, if you hook this PTE and modify it and so that it points to your page, then you can modify on hook KE bug check or other specific routines so that, yeah, basically you can bypass PatchGuard by modifying this PTE. So this is to prevent that. Yeah. So a trick is used to do so. To flush the TLB. I wanted to point it out because I found it really interesting. It's actually a side effect of the Intel instruction. When you modify the CR4 register, it will flush the TLB. So I just look at it and I found it interesting. I wanted to point it out. Next, it will rewrite some critical routines, such as KE bug check, of course, and other routines that are used to basically set up the entire process of the KE bug check blue screen of this. And this is important, of course, because some old bypasses used to hook this function and restore the original state of the system so that no blue screen of this would be triggered in any way. So in this case, it just means that if you hook this function, your hook will be rewritten with the original code before triggering the check. So that's a good way to prevent a hook. There is a last anti-debug that I found interesting because also I don't know why, but it will overwrite the db2print function with the ret instruction. So basically it's saying to the attacker, no, you cannot print anything at this point. I'm not sure why, but yeah, it's an anti-debug. And it will also clear the stack so that even if you find a weird way of restoring on hooking KE bug check, you won't be able to restore the stack. Yeah. So this is how the version routines works. So now you have a good overview of from the initialization to the blue screen of this, and we may explore how to disable it. I developed a driver to disable it. I think it's working, but we'll see. So let's have a look. This is the overly simplified diagram I showed you at the beginning, and I just want to complicate it a little bit by adding two slips. And the idea is that at any time, PatchGuard will be in one of these states. So basically, it will be either rearming or sleeping or check. But in our case, we only want to look at the sleep because the check is probably quite fast and the rearming is also quite fast. And even though you get on the check, then you just have to relaunch again. And yeah, you'll get some part when PatchGuard is sleeping. So this is the objective. In our case, we will disable each sleeping thread. So the first thread we need to disable are the ones that are already launched. So basically, these sleep are already in the verification routine, and that's why it's there is a square around it. So how to disable the sleeping threads? Basically, we will loop through all the threads on the system and then win their code stack to find the check routines. Actually, at this point, we know all of them. We know all of the check routine. We know where every sleep are performed. So we just have to look and look at the stack and find the pointer that belong to the check routine. And when it's done, well, you just have to set timers to infinity, and this will allow to disable already many methods. So what about the next one? Next one is the one that is hiding from the beginning. So basically, the verification routine is not launched already. So for example, for method, so we'll see for other methods here. For example, for method 0, which is a timer, you just have to go, as I said, through the timer restant tree, find the PatchGuard context and disable it. For method 1 and 2, which use entry in the process register control block, you just have to knob these entries so that the legit routine will only think that PatchGuard is not activated this way. And for the fifth method, well, you just have to patch back the hook from PatchGuard to put the original legit DPC. And this will disable all of these methods. So what about the two new methods? The two new methods are actually interesting because I said before they use a global PatchGuard context structure. But what is interesting here is that they do not perform the check of the global PatchGuard context structure. The other method does. So basically, at this point, we disabled all methods that check the global PatchGuard context structure. So at this point, it's basically open bar to modify this PatchGuard context structure. So this is, well, you just have to find a way to modify it so that the other methods are not launched. By the way, you can also modify it so that you can protect your code if you want. Yeah, I didn't detail it, but yeah, basically it's open bar, so yeah, just have fun with it. So how to disable it? If you look at the beginning of verification routine, for example, the callback verification routine, one of the first check is done is whether or not the size of the already checked structure, no, not the size, the number of the already checked structure is above the value, and if so, it will exit properly. But as I said, this value is user control. We can patch it as we want, and we just have to put like 2000, and it will work, and it will exit properly. For the KISW injury dispatch, one of the first check is done is an allocation, which use user value. This user value is supposed to be the size of the state of the algorithm SHA 2056. But we can also give like FFFFFFF on the X allocate pull with tag will fail, obviously, for obvious reasons. Yeah, I missed some F, but yeah, you can guess that there are 64 bits of F. And yeah, in this case, it will exit properly. So this is how you can disable this method. So basically, we developed this, and yeah, it seems to work. So there are still some problems, of course. It's still a POC. I'm not a developer, actually. My first driver was like 5 months ago. So I have some problems, some bug checks, which are not related to PatchGuard, which are related to APCs that I don't manipulate well. But yeah, basically, it disabled PatchGuard, but I need some more work to do. There is a huge precondition, which is it's kernel specific. It's specific to a specific version. It's kernel specific, so basically I have a lot of hard-coded offsets in my driver, which will change, no doubt of it, will change between 2 versions of Windows 10. And yeah, still a lot of work to make it more reliable, but yeah, it's very interesting. Yeah, that's it. So that's it for our proof of concept. So now let's conclude a little bit. Basically, the more initialization methods there is, the more work there is for the reverser, of course. PatchGuard use an incremental way of developing. So basically, each time someone finds a bypass, Microsoft just add a new method. Yeah, basically, it say no, you didn't bypass all of it. Bypassed all of it. So this is how it works. So, and if you find a bypass, Microsoft will probably ask whether or not to be sure that you bypassed all of the thing. The thing is, there are some breadcrumbs, a lot of breadcrumbs. I found some recently, actually. For example, when you delete a process, there will be an identity check. These don't use any context structure. This is just in the middle of PSP create process delete. And this is okay because it actually uses global variable to store the result of the checksum. So in this case, to bypass this way, you will have to it's okay. You will have to just compute again the checksum with your patched IDT, and it will be okay. So and this is initialized in CMP initialized transaction. There is also the key service descriptor table that is checked, and it is initialized in CMP init relay delay ref KCB engine, and it is checked when you initialize user APC. And there is also a trick from KI verify scope execute, but in this case it will initialize a PatchGuard context, but in a way that error disabling POC disabling it. So the idea is that PatchGuard is not obfuscated. At this point, I'm not sure why. I think it's because it must be fast, but it's not obfuscated. The code is here. Yes, it's pretty huge because they inlaid all of the things, so there is a huge function, but basically, usually, you look at the graph and you see, oh, okay, this is a huge part of the graph, but it's only in a location, and this is okay. So once you read it, a lot of time you will just skip the parts you already know, and it will be, I won't say obvious, of course, but yeah, you tend to recognize some part of this function. But the other thing is that it's hidden and it uses some tricks, a lot of tricks. There will be a white paper with much more details in it. Redacting it, it takes a long time, but yeah, I'm trying to as soon as possible. Yeah. As our conclusion is that not a single debugger was used during this analysis. We used timeless analysis. So basically, all anti-debug stuff were bypassed in a second. We don't need to. And yeah, we didn't have to launch like 10 times just to get any specific state. We just had to, the idea is that I analyzed and then watch back to the trace. Feel free to go to the run booth in the hallway if you want to. Then there are special thanks, close and acknowledgement. Of course, OffensiveCon for giving me this opportunity. Brisdang for some proofreading and stuff. And many people, such as Tonda, Mark-Olaf, Artem Shishkin, Skywingske, and Peter Benes, and my boss for letting me work on this awesome project, my coworkers, and people from OSR and many more. So, yeah, this is basically it. Do you have some questions? Oof.
Okay, first of all, very nice research, thank you. And then I keep hearing about HyperGuard being the next level of replacement of PatchGuard. Have you ever looked into that at all?
Not yet, sorry. Okay. Not yet. I don't know what works yet.
More questions? So here's an obvious one. How much time did you sink into it?
A lot, like maybe 4 months. Yeah. Yeah, because I had to level up on many stuff. Like, if you know how to write drivers and everything, it will be way quicker. And I didn't. So, yeah, the state of art is pretty long to analyze too. Okay.
Okay.
Feel free to ask me some question more
caffeine
outside if you want.